So welcome for today's session. So today we will going to discuss on the universal gates, that is nothing but the Nand gate and NOR gate, and we'll try to apply these universal gate for the various circuits. It means we'll try to write the logical circuit by using only these universal gates. So before that we'll see some of the proofs. So let us hit back to our screen here. Now there are few couple of proofs that we'll do before going to this. So that is, the first one is that what is 0 XOR with A bar? Let us find out what is this. So 0 exclusive with A bar. So what is the A exclusive XOR equation? So A exclusive B is nothing but we have, that is A bar B plus A B bar. This is our XOR equation. Now if you write the same equation, then it means A bar, here this is A, and let us treat this as one more variable here, so you can call this as B as well. Anything is fine, even if you write B bar into A plus A bar B, it's all same. So then it is 0 let us define with some new variables. So this, let us call this as C, and this is call it as D. Then we know that it is A bar, that is nothing but here there is C bar. So C bar, here it is C, is C bar will be 1. Then C bar into A, so now that is nothing but D. So this we'll write it as A bar itself, plus then it is 0 into B bar. So now I'll get here, it is D bar is nothing but, so it is A. So what do we get here is that 1 into A bar and plus 0 into A. If A is 0, then it is 0. If A is 1, still it is 0. So it means the entire term is 0. So now this will result in A bar itself. We know from the Boolean theorem that 1 into A bar is nothing but A bar itself, because we don't know what is the value of A. It's like just like A into A. A into A is nothing but A itself. So likewise A into A bar is also A bar. So it means 0 XOR with A will result in A bar, right? And let us take the second one. What is 1 XOR with A bar? So 1 XOR with A bar. So let us take this as C once again, and this we take it as D. So now if we write this in general terms, that is C bar into D plus C into D bar. So now let us substitute this like C and D bar. So C bar means this is C, means then C bar is 0, and D is nothing but the A bar, plus now if it is 1 into D bar is nothing but it is A. So 0 into with anything is 0. So now we are left out with return A. So it means 1 XOR with A bar will result in A. These are the important relations. You have to remember this. So we are just showing the proof here. So now let us write the remaining terms on this side. So third one, let us take it. So now let us see what is A x nor with 0. So A x nor equation, we know it is actually A bar into B bar plus A into B. So this is our x nor equation. So if same thing if you apply here, so if you call this as A and this as B, then what do we get here is that A bar into B bar into B bar plus A into B. So here A is A itself, so A bar, so I'll write it as A bar. So B is nothing but here the second term, that is B, so it's a complement of 0 is 1, so plus A into B, so it means A into 0. So A into 0, again this term is become 0, so only we have this term. So as we have seen before, that is 1 into A bar is A bar itself. So it means this will result in A bar. So A x nor with 0 is equal to A bar. Now let us see the fourth one. What do we get here is that what is A XNOR with 1? So A XNOR with 1, so let us write again, so that is A bar into B bar plus A into B. So A bar is nothing but, so we'll write here A bar, so B bar, so if this is B, then B bar will be 0 plus A into B. Sorry, so here B is nothing but here 1, so this is nothing but, so A into A bar into 0 will get 0, so A into 1 will get it as 1. So it means this is equal to A itself. So these are the couple of things which we will use. So this is equal to what? So this will result in A bar, so this will result in what? A, and likewise we are written for all of it. So these are the important proof. Now let us say this with one more example. So this kind of examples will come in examination. Let me save this page. Okay, let us take a new example here. So here we have to determine which of the following are equivalent to A exclusive B and which is equivalent to A XNOR B. So that is the question. So let me write the question here. So question is to determine which of the following are equivalent to A XOR B. I'll write like this: A XOR B, and which to A XNOR B. Okay, so we have the first one here is what is A bar exclusive B. So A bar exclusive B, let us see what it is. So now let us treat this as the new terms, just to avoid the confusion. Let us call this as C and this we call it as D. So now we know the XOR equation, so we'll write this as C bar into D plus, it is D, C bar into D plus C into D bar. So now let us substitute this. Now C bar, so this is C bar, so bar into bar, so I'll get it as A, and here I'll get it as B as it is, plus now here it is C A bar and here it is D bar, it means I'm getting here B bar. So this is nothing but I'll get A X nor B equation. So it means this is equal to A X nor B equation. Are you getting this? It's very important. So if you just complement this, if you write A bar exclusive B, it means you can convert that. Ultimately you will get this equation. If you XOR A bar with B, we will get as X nor equation. So that is what it means. So this first one. So likewise, let's see the second one here. Second one is that A X nor with B bar. Now we'll treat this again with the new terms here. This is, we call it as C and this we call it as D again. So we know the XNOR equation. So that is given as C into D plus C bar into D bar. So then if you substitute here, so this I'll get it as A B bar plus this C bar is nothing but, it means it is A bar, and D bar is nothing but I'll get here bar and bar, it will get cancelled, so ultimately I'll get it as B. So this is nothing but it is A exclusive or XOR B. So this will result in A XOR with B. So now let us see what do we get for the third term here, that is for A bar exclusive, sorry, XNOR with B. So what do we get for this thing? So let us again call this with new terms here. So let me call this as C and this as D. This is C and D term. So now we'll write this XNOR equation, that is C into D plus C bar into D bar. So then I can substitute for this. So C here it is A bar, D is B, plus C bar is nothing but double bar I'll get, so I'll get it as A itself into B bar. So this is again will result in the same thing. So this is nothing but A XR with B. So it means if we just complement any one of the term in the XNOR equation, so then I'll get exclusive OR equation. So that is what it means here. So it is A exclusive B. Now let us take the fourth one. So fourth one is, now here we have complemented A, let us complement B here and let's see what we get. So A exclusive B bar. So what do we get? Let me call again with the new terms here, that is C and D. So I'll write this is equal to C bar into D plus C into D bar. This is nothing but, if I substitute here for C, I'll get it as A bar into B bar plus I'll get it as A, I'll substitute for C, so it is A, then here D bar, so it's B bar again, so B double bar, I'll get it as B. So this is nothing but again we got it as A X, sorry, it's A XNOR, so symbolically it is represented like dot with a circle, so A XNOR B. So this will result in A XNOR with B, right? So now the last thing we'll see, very interesting one. So let us take the fifth one here. So let us take here as A bar. Let's do this and see what do we get. Let us complement both of the terms for XR equation and see what do we get. So I'll call this with new terms here. So C and D here, just to avoid confusion. So it is C bar into D plus C into D bar. So if I substitute here, so A double bar, I'll get it as A, then D is B bar plus here C, I'll get it as A bar, so D bar is nothing but B, so I'll get the same thing. So it means I got it as A exclusive B itself. It means if I complement and XOR that, I'll get A exclusive B, right? So these are the couple of interesting proofs. Now we will look into the universal gates, how to obtain or how to draw the logical circuits for all other gates using basic Nand gate and NOR gate. So let me save this page here. Okay, so I'll take the new page. So here the topic is realization gates, realization of gates using Nand gate. Okay, so we are going to realize all other gates just by using Nand gate. So before going into the Nand gate realization, so what is the Nand gate equation? So Nand gate equation is that, so A into B bar, this is the Nand gate equation. It means it should be in a product form and it should be, the product should be a complement one. So that is the Nand gate output should be in this form. So now if I want to realize a NOT gate, for example, what is a NOT gate equation? So NOT gate equation is equal to A bar. So now if I want to realize this A bar, so input is A, then output I should get it as A bar. So with the last theorem of our Boolean that we have seen, if you put double bar to any variable, so that will result in the same variable. Can you tell which law is that we had discussed before? So that is from the involution law. We'll get the complement of anything is the same thing itself. So now to get that, it's very simple, it's straightforward. In this case, if you want to realize this using Nand Gate, so let me go with very basic. Now this is our Nand Gate structure, a single Nand Gate with a bubble here. So now the output, I want this as A bar. So let us join both the inputs and I'll give to a common input, that is A. So if you look into the truth table here, so that is A into A. So and Y is equal to A into A bar. Now it is in the same form like A into B bar. So now if it is 0 into 0, so 0 into 0 is 0. Now it is 0 in so if it is 1 1, I cannot write 0 0 0 1 1 0 because both are A itself. So when it is 1 1, so I'll get it as, sorry, this I made mistake. When it is 0, I'll get its complement as 1. When it is 1, I'll get a complement as 0. Right? So now let us look into the second one, the AND gate. So the equation of AND gate is A into B. So how to get this A into B? So now to get into A into B, we are going to apply the involution law. So that means just apply this double bar, because this is nothing but the double bar results in the same thing, that is A into B itself. So it doesn't going to affect much, but this will help in simplifying our NAND gate. So if you look into just this term with single bar, so this is in a NAND gate form. So it means we can just write this as one simple NAND gate. So what do we get here? So we'll apply input A and B. So output is A into B whole bar. If I leave at this point, then this is not an AND gate. This is not an AND gate. It will become NAND gate. Ultimately, I want the output in the form of AND gate. So if you want this to be an AND gate, so there is one more complement. To get one more complement, you have seen from this NOT gate. So if I apply the same input again to one of the NAND gate, I'll get the complement of it. So this output I'll apply to a NAND gate here, and I'll get an output like A into B. Already there was a bar, now there is one more bar applied. Now this is nothing but this is equal to A into B. So it means I can use my NAND gate to obtain an AND gate results. Are you able to follow? Are you all listening? Okay, fine. Any doubts so far? Any queries? Okay, if there are no queries, we will continue. Right, so now let us go for realization of the third one, OR gate. So what is the equation of OR gate? So equation of OR gate is A plus B, right? So now I have to realize this using NAND gate. So I told you it should not be in a product, it should not be in a sum form, it should be in a product form. So what do we do now is, again we'll apply this involution law. It means we'll apply the double bar for this. So by applying the De Morgan's theorem, so I'll going to break this first bar. So then what do I get here is that A into A bar into B bar whole bar. Do you agree with this? A bar into B bar whole bar. Now we will keep in this form because ultimately you just see this A bar into B bar as the product, as one more variables as C and D. So now it is in the form of C into D whole bar. Now it is an AND gate form. Ultimately we have to bring this in an AND gate form. That should be our ultimate goal. So now if you are able to bring this in this form, so now it's just a realization. So now realize this. We have two inputs here, that is A and B. So I'll just move this term, I don't have place. Okay. So this is my A into B input. Now first, before proceeding to a plus b, so first what I need to do is I have to complement this. So how do I obtain the complement of a? So just apply the same input to both the inputs of the NAND gate. I'll get the output as a bar. So likewise, if I apply for both the inputs of NAND gate the same variable b, I'll get this as b bar. So now I got a bar, I got b bar. Now you combine these two using one more NAND gate. So what do we get here? So we get finally this is a bar into b bar whole bar. Now you break this one more outer bar and see whether you'll get the OR gate output or not. So if you break this, so I'll get a double bar plus b double bar. I hope you understood the De Morgan's theorem. So De Morgan's theorem is nothing but if you break the bar, the sum will become product and product will become sum. So now this is nothing but a plus b. Sorry, what I'm writing. So this is equal to a plus b. So exactly the OR gate output. So this is the uh, OR gate circuit using the NAND gate, or OR gate realization using NAND gate. So in the examination they will ask you to derive or to draw the or to realize the OR gate or any other gate using NAND gate or NOR gate. So in that case you have to follow this kind of steps. Okay. So now let me save this page and go to next interesting cases. Okay. So now we'll talk on the next fourth one, realization. So let us realize the NOR gate. Let us realize the NOR gate. So NOR gate equation is what? A plus B bar. I need to get a complement. So to get this, once again what we will do is that, so A plus B bar is already there. Now once again we'll apply our involution law, that is the double bar, and let's see what do we get here. So now I'll break this A bar into B bar into double bar. So now it is in a perfectly in a NAND gate way. Let us keep it as it is and just see. And now realize this, it should be in this form. Don't simplify this further. If you simplify this further, you will not get anything. Ultimately, you'll get back the same, this equation. So now let us take the two inputs, that is A and B here. So first take the complement of A. We know how to do it. So just apply for both the inputs of NAND gate. You will get this as A bar. So then we'll apply this to the NAND gate. We will get this as B bar. So then let us combine this to one NAND gate. This is A bar into B bar whole bar. If you simplify this, we will get this as A plus B. We will get OR gate, but we do not want OR gate, we want NOR gate. So it means if you see there is a one more bar here. So now with one NAND gate we got this one bar. So you just apply, just once again you complement this because there is a one more bar. So that tells you to do one more level of complement. So let's do this one more level of complement here. So then we finally get this as A bar into B bar into whole bar into whole bar. Now if you break these terms, you can see that you get A double bar plus B double bar and one more third bar, that is final bar. So that is nothing but it is exactly the NOR gate, A plus B whole bar, right? Okay, now let us look into the XOR gate. You can also try for XNOR later. Let me save this page because I need a little more space. I'll take the new file here. So next fifth one we have taken, that is realization of XOR gate using NAND gate. So what is the equation? So equation is A bar B plus A B bar. So this is the equation. So same process again. Let us apply the involution law, that is apply the double bar to this. A bar B plus A B bar. You apply the double bar. So now A into B whole bar into A into B bar whole bar, because we have broke this first bar, so this we have broken into only two terms here, so this plus will become product, means the sum will turn into product. Now let us keep it in this form. This is perfectly fine. If you look into this as the combination, as the new term, that is C and D, so then you can see this as C bar. Anyway, I'll take this entire term as C, so then I'll get this C into D bar. It means it's perfectly in the Nand gate form. So now it's perfectly in the Nand gate form. Let us realize this. So first what we need to do is we have to go step by step. First just find the complement of A, then take the complement of B, then we'll see each of these terms. So we have the two inputs here, so let us write this. This is A and this is B. Okay, so now just find the complement of this. You apply this to Nand gate here. So I'll get an output as A bar. So then I'll take the complement of B by applying B to both the inputs of Nand gate. So I'll get here B bar, right? So now I get A bar and B bar. Now if you look into this term, it is A bar into B. So A bar is here. I need to take B. So I'll take from here, that is B, and I'll apply it to the input of my Nand gate. So then I'll get this output as A bar into B whole bar. Perfect. So now there is another, let's come to the another term. It is A into B bar. So B bar is here. Let us apply this to A bar term. So I'll just put a thick dot to show it's a connection, because if line passes through this, it doesn't it doesn't mean that it is having a connection. Only the thick dot will represent there is a connection. So now this is perfect. Now it is A into B, A into B bar whole bar. So now it is done. Now finally we have to AND this with one more NAND gate, and then that will give us a final end output. So this will give the end final output, that is what? That is A bar into B whole bar into A bar, A into B bar whole bar, and then finally one more bar which we got from this last NAND gate. Now if you break these terms, what we get actually is that, so A bar into B double bar, you break this bar, so we'll get plus, so then A into B bar, we have one bar here and we got one more bar, so a double bar. So we know that this double bar get cancelled, so ultimately we get the equation that is A bar B plus A B bar. Interesting? Yes. So like this you can realize any circuit. It's not only the gates which you have to realize. So next examples we'll see that in the coming classes, that you can realize this for any Boolean expression or any given expression. You can apply this NAND gate realization. It's very interesting. Fine. So hope you have able to follow this. Let me save this page. 76. Right. So now let us look into the next thing. Realization of XNOR gate, I will leave it to you. Realize it using NAND gate. So that will be a kind of homework for you. So next I will go for realization of gates using NOR gates. Now before going into realization, we have to understand what is the output of a NOR gate. What is the equation of the NOR gate? So NOR gate equation is that it is A plus B whole bar. So it means anything we have to bring it in this form. If you are able to bring in the sum form, any equation. So then we can realize the any equation in the using the NOR gate. Okay. Um, Now let us look into the first one, simple NOT gate. The simple NOT gate output is just a bar. So like NAND gate, NOR gate also, if I connect both the inputs of NOR gate with this common input, I'll get, if I apply this A, I'll get this output as A bar. So how is that? So just see. So I have the two inputs, that is A and A. So this will give me A plus A whole bar. So it means if I apply this 0 and 0, so 0 plus 0 is 0 and complement is 1, and 1 and 1, then what happens? 1 plus 1 is 1, its complement is 0. So that is what I'll get here. Alright. So now let us look into the second one, realization of AND gate. Realization of AND gate, or let's talk about first realization of OR gate, then we'll go for AND gate. Realization of OR gate. So we know the OR gate equation is very simple. It is A plus B. So how to get this A plus B? So then it's very simple here. A plus B, you apply the double inversion and we'll get the A plus B itself. It means you take out this bar, I'll get A plus B. So it means it's perfectly, now if you look into this first bar, it is exactly in the NOR equation. Now if you complement that output with one more NOR gate, we will get the OR gate. So let us take the two inputs here and connect to the OR gate. So what do we have here? So we have A and B. So then I'll get this as A plus B whole bar. So I want to remove this bar, so it means I have to complement this again because I just want A plus B. So then if you apply to one more NOR gate, so I'll get A plus B double bar. So A plus B double bar is nothing but A plus B itself, right? Now let us look into the third one, that is the realization of AND gate using NOR gate. So what is the equation? So equation is that y is equal to A into B. So now to bring it in A into B in the sum form, so let us apply this double bar. So once we apply this double bar, so let us break this first bar. So then I'll get this A plus, I'll get this as A bar plus B bar whole bar. Now it is perfectly in the NOR gate form equation. So let me move these equations, this circuit to the left side. Okay, so now before applying directly to get this, so first we need to find the complement of A, then complement of B. So we know how to get it with the previous NOT gate example. So just pass through this two inputs with the same variable. I'll get here as A bar. So likewise, you get this here B, then we'll get here B bar. Now you combine this. So when we combine this, we know we'll get this as, so what do we get here? So we'll get here A bar plus B bar whole bar. Now let us break this bar and see whether we'll get AND gate or not. So we'll get A double bar into B double bar. So it's perfectly, it is an AND gate output. So it is A into B, right? So this is how we can simplify this, the circuits. So let me save this. Page 77. So let us go for the next fourth one. Now let us realize the NAND gate using NOR gate. So let us realize the NAND gate. So what is the equation of a NAND gate? So NAND gate equation is that it is A into B whole bar. So to get this A into B whole bar, so it it is A into B whole bar, you write it. Now we will apply our involution law, that is double bar. So now you break this first bar here, so you see what you get. So A bar plus, we'll get B bar. Now we have the two bars here. Now this, if you say with this another whole bar, the first one, it is in perfectly in the NOR equation form, and now we can get this. So first we have to find the complement of A and complement of B, so that we can find it by applying the same input to a NOR gate. That is for both, for all the inputs, if you apply the same thing, we'll get it this as a complement. So likewise you get it for B here. So then we'll get this. So this is input is B and this is B complement. So now we got this. Now let us combine this. If you combine this, so what do we get here is that A bar plus B bar whole bar. So when you simplify this, we'll just get A plus B. We do not get A plus B bar. So it means there is a one more bar here. We have to complement this output. So to complement this output, you apply as input to one more NOR gate. So then I'll get this as A bar plus B bar double bar. So now if you simplify this, so if I break this bar here, so what do I get? A double bar into B double bar into whole bar. So A double bar is nothing but A and B double bar is nothing but B, and ultimately we have a final bar. So now this is perfectly an output of a NAND gate. Now let us realize the XOR gate using NOR gate. Let me save this page here. It's page 78. So before going to that, let's see how much time you're left out with. Okay, we are left out with the 9 minutes. I'll try to cover it. So the fifth one is nothing but the XOR operation. So XOR, we know the equation, it is A bar B plus A B bar. So now right here, A bar B plus A B bar. Now let us apply the double bar on this. And now we'll see that when we break this, what do we get? We'll get this A bar B whole bar into A into B bar whole bar with one more bar. Now we don't want to put this in a product form, we want in a sum form. So what you do is you break these inner terms here. So if you break these inner terms, I'll get A double bar plus B into A bar plus B double bar. So B double bar is nothing but B itself, and we have one more whole bar here. So now this is in a fine in some form, so I need to break this one more bar here. So if I break this one more bar, so what do we get? So sorry, this is B bar. So A double bar is nothing but A plus B bar plus A bar plus B whole, now this is whole bar only on these terms. Now you can see this as C and D, so then it is something like C plus D whole bar. So it is in a NOR gate form. Alright, now it is perfect. Now we can go ahead for design of the logical circuit. So we need two inputs here, that is A and B, and we need to take the complement of this, because here there is A bar and here it is B bar. So let us take quick complement of this. Okay, fine. Now it is A plus B bar. So this is B bar and this is my A bar. So I'll take from here and I'll connect to this. So what I get here is that my A plus B bar whole bar. Alright, So now I have to connect this with one more XOR gate here. So what do I do is I'll take from here one input and I'll connect here. So this, I'll get this as A bar plus B perfectly in a whole bar. Now I have to add these terms here. I'll add these terms. Now if I add these terms here, now this is A bar plus B whole bar plus it is A plus B bar whole bar. But when I perform the OR operation, ultimately I want only in this form. This is the right form. But what do I get here is that I'll get one more whole bar. So to take out this one more whole bar, I need to pass through this one more NOR gate to take out that bar. So ultimately I'll just take on this bar out. So when we try to simplify this, what we get here is that A bar into B plus A into B bar. So ultimately we'll get back our XOR gate. So this is how we can realize any equation, any expression using the universal gates. Okay, thank you for joining for this session. So we'll continue with the next session.